You introduce him. This is Dr. Mark Willman. I've known Mark for, about 10 years now? More. Yeah. Anyway, since he started as a graduate student over at the University of Hawaii. Mark's been in Hawaii for over 30 years now. He's been in several bands apparently on the Big Island, and at night you can hear him playing his guitar if the weather is not good. He's had several businesses over on the Big Island, orchid grower, he had a dive shop, and then he decided he wanted to go into astronomy. He went over to he got his PhD at the University of Hawaii Institute for Astronomy in Manoa in 2010, and the subject he was an expert in is weathering of asteroids. So this is where asteroids become redder due to the solar wind and the environment. Yes, redder. Correct?
Asteroids get redder?
Yes.
S-type asteroids.
Okay. Yeah, the question was, did I say redder? Okay, so, and now he worked for the University of Hawaii 88-inch telescope, and then we somehow snuck him out that door and got him over here as a Pan-STARRS observer. And tonight he'll be talking about the gold rush in space. And so let's give him a nice Maui welcome.
Thank you. Hello, everyone. Welcome to those in the house and those joining us online. Tonight's topic is humanity's use of resources and how that is driving us into space. Some of you may recall when in the mid-20th century people began exploiting near space, Earth's orbital space. But now we've come to the point where corporations are ready to push into deep space, leave the Earth's orbit, and for the first time go out and try and make money. And so this is the beginning of a new era, a momentous transition. And so let's review resource use in prehistory as a start. Now, when I was putting this talk together, I thought of the points I wanted to make, and I gathered appropriate slides. But then I realized you needed a bit of an introduction, so I started to write out some context, some background. And I went back farther and farther, and ended up with this. This is too much to memorize, so if you'll indulge me, allow me to refer to some notes here briefly, and then I'll show you some pretty pictures here. So, gather around the campfire, children. Let me tell you a story. It happened long, long ago and far, far away. It has all the ingredients you want in a story. There's fighting and romance and great adventure. And thank you, Benjamin Franklin. The only part I can't tell you is how it ends, because it's still in progress. We all hope it has a happy ending, but that depends on whether the heroes can cooperate to escape the trap they find themselves in. This is the story of human beings. Paleontologists tell us that anatomically modern humans appeared 200,000 years ago, and like the species before them, they survived as hunter-gatherers off wild plants and animals. Archaeologists say they reached cultural maturity. That's the anatomically modern humans, not the archaeologists. As you know, archaeologists are not culturally mature. 50,000 years ago, so somewhere in that range is our beginning. Then there were a series of glaciations, and when the last one ended 11,000 years ago, we made the leap to agriculture thanks to two factors. One was the necessity created by exhausting the resource of the big game. Think woolly mammoths here. We wiped them out. And two, the opportunity created by the end of the glaciers, which made Mesopotamia ideal for another resource, growing grain. So people got better at growing grain over several thousand years. And by 6,000 years ago, there was a grain surplus, and the first civilizations arose. With benefits like steady food, better housing, more varied social life, but also negatives like class division and warfare. Although we accept warfare as normal, it's abnormal. Only around for 6,000 out of the last 100,000 years, a few % of our existence. In the historical period, civilization evolved until our current economy, capitalism, appeared 500 years ago, producing a population explosion and huge resource demands. Then the Industrial Revolution accelerated human impacts on the planet a mere 150 years ago. The effects include pollution like atmospheric CO2 buildup causing climate change and exhaustion of resources like oil. This background leads to our topic, another resource being exhausted, metal. Because of prodigious human expansion and high per capita consumption, we require vast amounts of metal. The most common metals on Earth, iron and nickel, form the bulk of the planet's core, but are inaccessible. The metal in Earth's crust mostly comes from asteroids. High-grade ore was used up after World War II. There's still a lot of low-grade ore on the planet, but demand is rising 10% a year, and continued growth will exhaust supplies in decades, not centuries. The price of iron ore has tripled from $40 to $120 a ton in the last decade. Now, iron is still relatively cheap, but platinum, our focus tonight, is not. It's also tripled in the last decade to $1,400 an ounce, more than gold at $1,300. Platinum and gold are roughly equally valuable. Platinum rises when the economy is good and there's industrial demand. Gold rises when the economy is weak and people sell off stocks. So sometimes one's higher, the other's higher. They switch back and forth. Stocks and bonds. This scarcity is what's driving the search for metal into space. 2 billion years ago, there was an asteroid strike in Canada that produced the Sudbury Basin, that's just north of Detroit, and made it rich in metals like nickel and copper. This is a region that's about 20 miles wide by 40 miles long, and they say that the ore-rich section is about 6 miles deep. It's very rich in nickel and copper, also has some platinum. There's platinum at concentration of 1 part per million. Now that sounds pretty low, but it's 200 times higher than the average platinum concentration in the Earth's crust. So 1 part per million is worth going after. South Africa has the world's highest concentration, 10 times higher than Canada, due to an extrusion from Earth's mantle. So I said most of the metals on Earth come from space, come from asteroid hits, actually. But we're sitting on a vast amount of metal down there. We just can't get at it. But South Africa has a unique situation. The metal actually came up from below there, and so it's quite rich. 80% of the world's supply comes from South Africa. However, iron meteorites falling on Earth contain more platinum than anywhere on Earth. Are there even higher concentrations out there? Another tantalizing possibility, could there be big solid chunks? That would be the ultimate jackpot. Okay, let's look at iron's properties. Platinum's properties. Hayden. We will shortly see here a periodic table, which we can thank Mendeleev for, from the 1860s. And at that time, you all remember the periodic table from. There's a periodic table on the back side of this door, right here. Okay, fantastic. We don't need no video. This is old school, great. So now when Mendeleev made this table up in the 1860s, there were a lot of gaps. Now we've filled in all the gaps, thanks to the 20th century. And we've even added a lot of new stuff here at the end. So the key point of this table, these columns represent elements that are very similar. So that's why they repeat like this. So all the elements in a column have similar characteristics. Now this column on the right end here is particularly interesting. These are the noble gases, helium, neon, argon, and so on, and they do not react almost at all with other elements. So they're very inert chemically, we say. Now, why is that? Well, because of their filled shells. You remember your atomic physics. You have a nucleus, and then you have electrons going around that. Now, the electrons exist in shells. So once you fill a shell, you get one of these noble elements. It's like an impervious, like a suit of armor or something. So for instance, helium has 2 electrons. That's the first shell. It's filled up. Then if you add 8 more in the second shell, you get neon. That has 10 electrons. The second filled shell, and then the third filled shell, and so on. However, if you're just one to the left, one column to the left or one column to the right of these filled shells, then you're either 1 electron short of a filled shell, sort of like 1 card short of a full deck, or you're 1 electron over a filled shell. So say 2 of those elements come together, like say sodium here would be a filled shell plus 1, and chlorine would be a filled shell minus 1. So when those 2 come into proximity, the interatomic forces then are very strong. They attract and they form a molecule, sodium chloride. And similarly, now if we come into the middle range here, far away from just overfilled or just underfilled shells, these are called the transition metals down here behind some artwork. So here you see our friend iron, there's nickel, copper, and so on. Down here is platinum. That's what we're after tonight. Number 78 has 78 electrons. It's far away from being just shy or just over a filled shell. It's highly inert. In fact, it's the least reactive metal on this chart. So this has a lot of valuable properties. Now, it happens to be right next to gold here, number 79. And right above it, we have silver. And we're not just interested in platinum tonight. We're actually interested in these 6 elements here. These are called the platinum group metals. Ruthenium, rhodium, palladium, osmium, iridium, and platinum. So these 6 are all very similar, highly reactive. They're also the densest materials that exist in the universe. Let's do a small digression on density here. I do. Let me grab a dongle. DVI and VGA. So, okay, back to the platinum group metals. We've got 6 of them here. And density, we were starting on density. Now, we measure density by comparing things to water. We say water has a density of 1. In fact, we define our units of mass by using water. Okay. Hooray. Okay, so water we say has a density of 1. In fact, we define it as 1. Originally, it was defined when the French made the metric system. It was defined as 1 gram. Thank you, JD. Okay, let's go back to full screen here. Slideshow. And bingo. Okay. So let's see. Water has by definition, has a density of 1 gram per cubic centimeter. But let's go to some units that are a little more compatible with the topic tonight, which is big rocks. So it turns out that 1 gram per cubic centimeter is the same as 1 ton per cubic meter. Now let's look at a cubic meter here. Here's a meter high, and a meter wide, and a meter deep here. So that's a cube. You don't see most boulders like cubes, so let's round that off. Let's squish off the corners and so on. Let's make a spherical boulder here that's 1 cubic meter. So that looks about like this. We'll call that our standard boulder. 1 standard boulder, 1 cubic meter of water weighs then 1 ton. What's next? Let's say rock. Say the rock around here, this lava rock. It weighs something like 2 to 3, yeah, 2.5, something in there. So we have our same standard boulder. That's going to be 2.5 tons. Goes up fast. Now let's go up to iron. The most common, iron and nickel are the most common metals on Earth. Iron has a density of 8. So our standard boulder is going to weigh 8 tons if it's made out of iron. If it's made out of nickel, it'll weigh 9 tons. if it's made out of what's heavy? Lead. We're coming to that. That's my punchline. Don't blow the joke now. This is lead, and you think, yeah, if you hold up a piece of lead, you know how heavy it is. That is the density of lead is 13. So our standard boulder made out of lead is 13 tons. Then if we go up to say gold, 19 tons. Now we come to osmium. Actually, osmium is slightly heavier. Let's hit platinum first. Platinum is 21 tons, a density of 21. Osmium is 22. So these two things, in fact, this whole group is exceedingly dense and heavy. What other properties do they have that are useful? Well, like I said, they're not corrosive because of this situation, this periodic table. So it's very valuable in industry where you have high temperature, corrosive environments. Then you want to coat your surfaces with platinum because it's very resistant to reactions. So that makes it highly valuable for specialized uses like that. Yep. Is what? Conductivity. High conductivity, yes. Let's see. How much platinum is produced every year? About 200 tons. The whole planet production, like I said, most of it comes from South Africa. The other two places are Sudbury Plain in Canada, and there's a place in Russia. The U.S. has almost no platinum. It has one small mine in Montana, but a few percent of the world's production. It's mostly South Africa. So every year, 200 tons are produced. Now, that doesn't sound like much, but it's even less than you realize because of the high density, right? Remember, it's 20 tons per cubic meter. So 200 tons is only 10 cubic meters. 10 cubic meters is a cube 7 feet on a side. Now, I'm about 6 feet, so 7 feet is here. Let's look at this corner here. Here's 7 feet out from the wall, 7 feet this way. So there's our cube right there, 7 feet tall. That's the whole platinum output of the globe every year. You see why this stuff is valuable. It's extremely rare. So it's non-corrosive. Of this cube here, about half is used for catalytic converters in cars. Now, car production is soaring, not in the U.S., but in China, India, and so on. All those people want to be middle class and drive cars, like Americans. So we are making a lot more cars, and so there's huge demand for catalytic converters. It catalyzes the reaction. So some of the most poisonous gases in your exhaust are broken down into less poisonous versions. Unfortunately, it doesn't get rid of the carbon dioxide, but that's a separate problem. So here's half our cube is gone for catalytic converters. Now, of the remaining half, 1/3 of the whole amount is used for jewelry. People find it very attractive. It's right next to gold here. Just a second here, we'll look at some pictures. And then the remaining 1/6 is used for other specialized industrial uses and for collectors, for investment. People do, the mints produce this, so you can buy it like gold bullion. You can buy platinum bullion too. Okay, let's move on here. There we are, platinum. Now, these are nuggets dug up from the ground, very rough. These are obviously smoothed off in stream beds. You'll often find nuggets of platinum like this that are found in streams. They were discovered in South America, actually, by Europeans in the, let's see, when was that? The 1760 or 1670, somewhere in there. The South Americans, of course, had known about them for many centuries, but it's very hard, very pretty, makes nice jewelry. You see the color changes from a kind of a white silvery color, looks very silver-like, to a dark gray. And you can actually find solid nuggets like this. Now, there may be a little admixture of osmium and iridium, the other platinum group metals in there. Actually, the word platinum comes from the Latin word Platina, which means little silver. So it often occurs in conjunction with silver in the ground. And the Spanish called it Platina. Okay, so that's what we're after now. That's what this gold rush is about. Now you're saying, well, what about gold? It's true, there may be gold in them thar hills in asteroids. Well, I mean, there is some amount of gold, probably on the level of platinum. Very low, but remains to be seen, really. So where do we find this stuff? If we're going to leave the Earth, we will have to go to the asteroids. Here are some asteroids. This is Gaspra. It's got a mean radius of 6 kilometers. That's about 4 miles. And the mean radius means if you squish this thing into a sphere, what would the radius be? So it's sort of an average. So, okay, here's an average across there. So that'd be about 8 miles in diameter across there. Here's Deimos and Phobos, 2 others. This one's bigger, so this one is maybe 15 miles across. And down here is Ida. It's about 16 kilometers, about 10 miles radius, so about 20 miles across. So the length here is probably about 30 miles long from there to there. There are much bigger asteroids we'll see in a minute, but these are a few typical ones. They get much bigger and much smaller. Okay, here's some fun and games. Ida in stereo vision. Now, I haven't tried this on the screen, but if you cross your eyes and look at these two until you see a third image in the middle, you should see this in stereo. I don't know if it works on this. Yes, it does work. It seems to work fine. There you go. Now, I know when you were a little kid, your mother told you, do not cross your eyes. They'll get stuck. She was wrong. She said, I remember I was told there was a little bone that would get stuck in your eyes, and you'd never be able to uncross them again. Folks, there is no little bone. So if you look at this in stereo, what do you see? Well, you see some craters here. These things take a pounding in space. It's a dangerous environment. Earth is a dangerous environment, for that matter. We get hit by asteroids all the time. Every day, we get hit by a basketball, on the average. And over longer periods of time, we get hit by bigger things. Like every month, I don't know how it goes, what the curve is exactly, but every 100 million years, we get hit by a really big rock that wipes out life, like the dinosaurs. So they come in all sizes, and they're going very fast when they hit. So they do a lot of damage. Okay, let's do the crash course in asteroid history. Just 5 or 6 points here. They were discovered, the first one at 1800 by Piazzi, an Italian, and he found the first asteroid, which is named Ceres, after the goddess, the Greek goddess of well, Ceres is the word we get cereal from. So now we're back to grain again. Now that turned out to be in an orbit between Mars and Jupiter. And for a long time, astronomers had suspected that there should be a planet there, because if you look at a map, which we will in just a minute, you'll see there's a gap. There's a big gap between Mars and Jupiter. And so it seemed logical. They weren't quite sure why, but it just looked like a pattern. And now, actually, there is support for that argument. As we've discovered extrasolar systems, other planetary systems, there is a principle arising. It turns out planets are densely packed. If there's enough room for there to be a planet, there probably will be a planet there. It seems like they're everywhere. That's another whole interesting talk, actually, for another time. Okay, 100 years went by, a century went by. And this was primitive telescopes, so it was very hard to do searches, not like pan-stars upstairs now. We canvass the whole sky every month. But these were harsh conditions. People had to stay up all night. Well, we still stay up all night, but the telescopes have vastly improved. Anyway, it took them 100 years to collect enough asteroids to be able to see a pattern, and Hirayama discovered what are families. We'll describe this in just a second. And then 50 years went by, and Zellner found out these asteroids have different colors. They have distinctions between them. 10 years went by. You notice we're picking up the pace here. This is due to 2 things, especially from here on. Big glass. We have huge telescopes now. And CCD chips, like in your video camera, that capture all the light that falls on them, essentially. So those 2 developments have revolutionized astronomy in the last 30 years, particularly in the last 20 years. So a guy named Dave Tolin, then, who is at IFA in Manoa, then did the first big survey of different colors and divided asteroids into 12 different types. We'll see those in a second. Then we're back to the Italians. In the 90s, Mazzari figured out a way of dating them, figuring out how old they were. And finally, in the zeros, Rob Jedicke, who was my advisor in grad school, and David Nesvorny solve the long-standing mystery of space weathering. We mentioned this. Somebody mentioned this earlier about the asteroids reddening. And so then I came along. I modestly included myself in this list. And in 2010, working with Rob Jedicke, I figured out the time scale. They had actually figured out a time scale. There was a mistake. So I found the mistake. And I think I have the correct time scale. This is a very interesting topic. Probably would merit another talk sometimes if people are interested. But there is a fair amount of controversy here. So there's two schools of thought. Rob and I represent the slow weather school. There's also others that represent fast weathering. Okay, here we are. I didn't say gardening. Gardening is the opposite of weathering. Weathering, we're on a tight schedule here, but I'll tell you about weathering. Weathering is the process by which the sun bombards the asteroids out here and causes the surfaces to slowly turn red. It brings up a layer of iron from inside the rock. It's like spray painting a beach red. You slowly redden. I think it takes hundreds of millions of years. There are some people that think it takes less than 1 million years. There's quite a controversy. Gardening is the opposite effect. Small meteorites come blazing in at high speeds, 5-10 kilometers a second, very fast, hit the surface, and churn up the dirt. So now they're digging up blue dirt from underneath. So these two effects are fighting each other. Weathering is trying to turn the surface red, and gardening is digging up fresh dirt, trying to turn it back blue again. So it's mathematically a little complicated what's going on. But here's the main belt. As we said, discovered around 1800. And we have the sun and the Earth. And here's Mars, and out here is Jupiter. In between Mars and Jupiter is the main asteroid belt. There's Ceres. That was the first asteroid discovered. Now this is the orbit of Ceres coming around here. And we don't show all the planets here, but inside, of course, we have Mercury and Venus and Mars. And then there's this huge gap to Jupiter. Now this is where people thought there should be a 1, 2, 3. We're the third planet. There should have been a fourth planet here. And actually, by rights, we now think, according to the mechanics of it, the physics, there indeed should have been a planet there, except for one thing. This is a really bad neighborhood because of Jupiter. Jupiter is 300 times heavier than Earth, and so its gravity is very strong. So Jupiter takes 12 years to go around in one orbit. The asteroids only take 4 years. So every 4 years they come whipping around, but then they pass Jupiter, and it gives them a tug and disturbs their orbits. So it's hard to assemble all these chunks of rock into a planet like should have happened. Actually, what's left here is just a residue, too, of what was originally there. There was originally maybe 100 times more material there, maybe up to 1,000 times more material. So this is the leftovers. There was a big disturbance in the early solar system. All hell broke loose. The giant planets out here were shifting around, and that really knocked the asteroid belt for a loop. So, but still, a lot of valuable stuff there. I'm basically doing one slide. Wait, we got to back up here. Per topic we had there, and this will just take a few minutes. Now look at these orbits. Another slight digression here. There's a convenient way to describe these orbits, and it's like as if they were in the orbits themselves occupied the space in a room. Consider the actual physical space in this room. We describe a position in the space, like this point right here, with 3 numbers, right? We say how far front and back it is, how far left or right, and how far up or down. So like that laptop corner there is 4 feet forward, 2 feet to the side, and 2 feet high. So 4, 2, 2. Those 3 numbers tell you that point uniquely. Now, you see you could extend this to a mathematical space. You could take anything that's described by 3 numbers and pretend like it's the space in a room. So these orbits, it turns out, have 3 numbers that describe them. The first is the size of the orbit, how big it is. We call that the axis. The second, A. The second is the eccentricity. Now, eccentricity is the opposite of roundness. So if you have a perfectly round circle, that has zero eccentricity. It's not eccentric at all. It's perfectly round. If you stretch that circle out into a long, an oval, and then stretch it more and more, you eventually stretch it all the way to infinity, it'll be a line, right? We call that eccentricity 1. So every orbit can be described with a particular eccentricity, tells you how out of round it is. So we have the axis is the size, the eccentricity is the out of roundness, and then we have the tilt. The planets are pretty much all in a plane because of how they originated in a cloud that collapsed, but it was spinning, so it flattened into a pancake, and that pancake is a pretty flat plane. But not perfectly flat. The planets themselves are tipped slightly, 1 or 2 degrees, a few degrees off, and the asteroids tend to be tilted more. They could be 5, 10 degrees, maybe up to 15 degrees tilted. So that's the third number. We call that the AEI. We call it the inclination. So those 3 numbers, axis, eccentricity, and inclination, we could view as points in a mathematical space, like in this room. And each point would represent an orbit. Now, they compiled they discovered hundreds of, or what are we talking about, asteroids, and in the first century. And by 1918, Hirayama was looking at this list of orbits with the AEI listed, and he started to notice something funny. If they were completely random, if these things were just all jostled around randomly, you'd expect those points to fill this room kind of randomly, like a gas. There'd be even amount everywhere, but that's not what he saw. This is what he saw. Here's the axis on one part of the room, one dimension. Here's the eccentricity and the inclination. And inside this box, we have plotted 1 point for all the asteroids. Now, this is a lot more. He had 100 or 2 asteroids at that point. We now have 300,000 or 400,000 asteroids have been numbered. They each have a particular orbit. We know precisely what that orbit is. We can find them anytime we want. They fall into these clumps. Now, what do you think? Why are those clumps there? Why is it not distributed equally? Anybody want to take a wild guess? Yep. Density, nope, and nope. Fairies, yes, that's right. Okay, I'll tell you. Resonance, nope. All right. Let's imagine you've got a single big asteroid. Let's say it's Gaspra we were looking at there. And here comes an impactor. 10 kilometers a second. Hits that asteroid. Breaks it into 100 pieces. Now what happens? You started with a parent body. We call it a parent asteroid. It had a single orbit, right? It was 1 point in this space. Then it broke into 100 pieces. Now you've got 100 asteroids. They each have individual orbits. However, because it's not an atomic bomb going off, it's just a collision. It takes all the energy basically to break this thing apart. There's not much energy left over to send the pieces shooting out. So they only move apart slowly, but they're moving fast through space, the whole group of them. Remember, they're going like 5 or 10 kilometers a second through space, 20 kilometers a second. They're moving very fast. But they're only moving apart slowly. So essentially, their orbits are all very similar, but they're slightly different. So there's going to be a little cloud of points here now that represent all those different orbits. And over time, the ones over on the right side there, closer to Jupiter, they're going to get tugged off a little bit more than the ones farther from Jupiter. So the orbits are slowly going to spread out. That's what happens here. So these small clumps represent recent, we call these families. This is a family that was created by a collision, and the orbits are all still fairly close together. But this big cloud here, this is an old family. The orbits have had maybe 1 billion years to spread out, and now the cloud is growing and growing. Eventually, the cloud will grow and fade into the background, and it'll disappear. We won't be able to identify it as a family anymore. But this is slightly simplified because we've ignored the background here. There are, of course, thousands of other asteroids here that are random like a gas. But these are high density. Well, density was partly a right answer because this is a high density in that space. But the cause of it is collisions. Okay, on to colors. 1964, Wood and Kuiper, Gerard Kuiper here, he was a famous Dutch astronomer. They found the first colors. They did 3 colors, blue, red, and green, and with three, they used glass filters, so they take pictures of asteroids through a piece of colored glass, and then you only get that light. So you see how much blue light is there, how much green light, how much red light, like that. And so then you can plot up, well, with three filters, you can plot up two colors because you have to subtract blue minus green and then green minus red. So then you make a plot, and you see different colors. So they found colors. But if you look at that plot, maybe I should have showed that, it jumps out at you that there's two groups. But they overlooked that. They didn't see that. It was the first time they had done it. It's funny how something can be staring you in the face sometimes, but the first guys that discover it don't notice it. If you go back now, maybe it's because we have hindsight, but it's so obvious there's two types. So it was another decade before Zellner noticed the two color groups. And here's Dave Tolin I mentioned, our own Dave Tolin from Manoa. And these are, okay, now Dave, here is the wavelength along the x-axis here. And the height above the x-axis is how bright. So he now has 1, 2, 3, 4, 5, 6, 7, 8 colors. So we had advanced by the 1980s. And this is called the 8-color asteroid survey. So he looked at, I think he had 600, or he looked at hundreds of asteroids, and he noticed they have, these are spectra, and so for instance this one is pretty flat, so there's about the same amount of green, red, and infrared. This is ultraviolet on the end. The human eye can see from about this is microns, about 0.4 microns up to 0.7 microns, so the eye can see from about there to there. Out past here, this is infrared, and on this end this is ultraviolet. But we can still take pictures in those wavelengths, even if your eye can't see them. So he noticed that there are distinct spectra. Basically, there's this flat kind, like C's. These are the most common kind, along with the S's, these two groups. And then there's these S's. This comes from stony originally. Now we call it silicaceous, and this is carbonaceous. These are dark. These tend to be reddish. You see, they come up on the red end here. They have a lot of red, not so much blue. So anyway, he noticed there was this pattern. Things fall into distinct types. And then ages, we already mentioned this. This was the first guy that figured out this method, Marzari, in 95. And again, here's this is 2 dimensions out of our 3-dimensional mathematical space we had. This is the size of the orbit, the axis we called it, and this is the eccentricity. So 2.8, 2.9, these are 2.1 AU, 1 astronomical unit is the distance from the sun to the Earth. So the asteroid belt runs from about 2 times that, 2 AU out to about 3 AU. And then, so Earth is at 1, Mars is at 1.5, asteroid belt's about 2 to 3, Jupiter's out at 5. So here they did a simulation on a computer, and they said, let's model a family, a particular family. And here's right after the explosion. This is time 0. This is 1 billion years later. You can see the family is spreading out, the orbits of the family. Now, this is not the physical position of the asteroids. This is the mathematical position of their orbits. So their orbits are diverging. And after 2 billion years, they've almost spread out so far they're starting to fade into the background. These X's are the background stars. Okay, that's our whirlwind tour of asteroids. Now, meteorites. How are they formed? Well, how are asteroids formed? They collect the same as planets. They start off small. It's a bottom-up process. So you start with little grains of dust, and they stick together and make dust bunnies, and then those stick together, and on and on and on. Finally, it builds up. Finally, you get something 100 kilometers across, maybe 200 kilometers across, and there's radioactive elements in there. At the beginning of the solar system, there's radioactive aluminum, aluminum-26, that produces heat. It has a half-life of about a little under 1 million years. So for the first 2 or 3 million years, there's a lot of heat generated, and all the metal and rock in this big clump that's initially just a big loose clump melts. It's so hot. And then the heavy stuff sinks into the middle, into the core here, just like on Earth. Like we have an iron and nickel core, And then we have our mantle, and then we live on the crust, which is silicates, is rocks. So that also happened on the big asteroids. Then they cool off after a few million years, and then they start getting hit by collisions. And it starts chipping away at the rock. And rocks go flying off. Those are future meteorites that might land on Earth. And you keep pounding away on this thing. You keep digging in. First you're getting through the rock layer. Finally you get down to the iron. And finally you're breaking off chunks of iron. So we get mainly two types of meteorites land on Earth. You'll see stonies, and you'll see irons. And this is the only source of free metal on the surface of the Earth. So ancient peoples valued these things. When they would find a chunk of iron, like in Africa, there's this immense piece of iron that's 30 feet long. And they built a temple around it. They couldn't move it, of course. But they dug out around it, and it's a ceremonial center and so on. It was a big deal. It's unknown stuff from the heavens. You know, it was very impressive to them. It's impressive to us. Here's a meteorite. This is a little piece. Here we are, 2 inches here, so that's about 2. So that's about 4 inches. So this is a rock about this size. You notice the surface is glazed. It only takes a few seconds for a meteorite to come through the atmosphere. They're moving very fast. So they heat up. The surface melts, actually. But it's so fast that the inside doesn't melt. So if you cut this open with a saw, you will see fresh material inside. It's just the surface that has this glazing. And we actually know where this comes from, a particular asteroid, 4 Vesta. That's the number 4 asteroid that was ever discovered. It's a big one. We can match it up by the colors, by the spectra. Here's an iron meteorite that's been cut open, so you can see the inside, and you can see some rusty spots here. And there's a nickel for size comparison. And now, interestingly, that is nickel, iron nickel. I mean, that's pure nickel. This is iron with some nickel in it, so we use this stuff from the heavens. We make our money out of it. And here is how you match up asteroids and meteorites. So we looked at some types, some spectra of asteroids. Here are some examples. These are types of meteorites we find on the ground. These are spectra we get from looking through telescopes at asteroids in space. So you see, you can match them up. This is a great simplification. There's a lot of complications that this glosses over. But in theory, in principle, you can match them up. There's a lot of difficulties when you actually try to do that. Here are some, okay, now back to our particular topic tonight, platinum. Here's 6 metals, and this shows the spectrum of them. Now, we're always changing units, unfortunately. We use nanometers and microns and angstroms. We cannot settle on them. So you just have to get used to it. But let's use our eye reception as a baseline. In what are we saying before? We said 0.4 to 0.7 microns. Well, now that in nanometers, that would be 400. 1, 2, 3, 400, 5, 6, 700. So this is our visual range. That's what your eye can see, only a little piece of this. But let's say now we want to do a survey. We cannot actually visit. There's probably, we've already cataloged 300,000 or 400,000 asteroids, and there may be a million. I mean, it's just a matter of what size you want to cut it off at as to how many you say there are. But we can't go out and prospect on each one. We can't send a spaceship. The fuel is prohibitive, and time. So when you're going to go look for this platinum, you have to do it through telescopes to start with. And so I was wondering, now, how would you distinguish platinum? Let's just say we were going for the jackpot strategy, and we wanted to find, let's just hope that there is a solid chunk of platinum, like there's one of our standard boulders out there. Oh, by the way, I should have mentioned the price. I did say it's $1,400 an ounce, but our standard boulder, well, what did we go? We went to our 7-foot cube. That's an annual production. That cube there is worth $10 billion. So 1 cubic meter, that's 10 cubic meters. 1 cubic meter is worth $1 billion. So our standard boulder made out of platinum is $1 billion. That's why people are hungry for this. So how would we find this? Let's just say we had incredible luck, and there's standard boulders of platinum floating around out there. You know how they were differentiated there? Maybe the platinum, because it's so dense, maybe inside the iron shell, when this big asteroid melted, maybe the platinum sank right to the middle. And when you beat off all the platinum, all the iron around it, then you expose that platinum core. And then that got broken into pieces, and now those pieces are floating around out there. That would be worth going to get. If you have to mine, go out there and mine. You know how expensive it is to mine on Earth. Imagine trying to mine stuff in space and then smelt it and then process it and so on. It's horrendously expensive. But the jackpot strategy now, that would be easy. Just go out, snag a boulder, bring it back. Ka-ching, $1 billion. Okay, so, yep. So how would we spot this? Well, now there's a problem, because if you look at the spectrum of platinum here, let's ignore this section for just look at this slow rising curve here. It turns out it's a lot like iron. In fact, here's a spectrum of platinum. So here's our 400 to 700 nanometers. Again, this is what we can see visually. This is the blue end of our vision. That's ultraviolet. Here's the red end, infrared. There's not a lot of identifying characteristics on this spectrum. It's pretty bland, isn't it? In fact, a lot of metals look like this in this wavelength range. But here's the smoking gun that I discovered when I was looking this up. If you follow this platinum curve here, the gray one, here we come up and up and up, smooth, nothing much to write home about. Boom, here's a hole. We call that an absorption band, but let's just call it a hole for now. And then it goes back to the same rise it was on. This hole is here, right here at, there's 1,000 nanometers, is at 2,000 nanometers. There's a hole there. Now you notice these other things are all different. Chromium has a dip also, but it's at 1,000 meters. Here's aluminum. It has a hole here too, but it's down here at 700 nanometers and so on. So if you look through a telescope and you got these spectra, and you see this hole here at 2,000 nanometers, that's the payday. That's what you want to go after. Then it might be worth mounting a mission to go after that. But first you got to identify these things. Okay, now on to the money. Let's get to pay dirt here. Business perspective. So far we've talked about the product we're after, platinum group metals. We talked about where they are, the main belt. Now actually, we're not going to go out to the main belt. That's too far away. So we're going to go to NEAs, near-Earth asteroids. There are some that come right close to Earth, and those are the ones we're looking for. In fact, I'm working on a project now with my buddy Nick Moskovitz from grad school, and he has a proposal in to NASA, which apparently just got funded, and that's called MANOS, which stands for Mission Accessible Near-Earth Object Survey. So actually last night I was up all night out in Kula observing on a telescope on Kitt Peak in Arizona. And it was a beautiful night. This is the kind of night you dream about. You know, you get nights where you're rained out. You get nights where there's high winds. There's Tommy in the back. He's one of my fellow observers. You sit through these nights and you can't open the telescope, the conditions. But last night it all came together on Kitt Peak. We got I think almost 10 hours of incredibly good data. And I tracked one particular asteroid. Now we're looking for asteroids that are mission accessible near it. So we actually want to find, there is this push, you know, Barack Obama, I think George Bush talked about a mission to Mars. Well, the U.S. economy is not so good now. The feds are under a lot of financial pressure. So they've downscaled. So now the buzzword is a mission to asteroids. It's a lot cheaper to go to an asteroid. First of all, they're closer. But even more importantly, there's almost no gravity on an asteroid. So when you land on it, you don't really land on an asteroid. You pull up next to it and park. And here's the asteroid, and there's no gravity, essentially. It's like 100,000th of Earth's gravity. So you save the huge expense of going to Mars where you have to drop down into that gravity well and then take off again. That's a hugely expensive in terms of fuel and the kind of ship you have to build and so on. So it's much, much cheaper to go to the asteroids. You just cruise out there, look around, cruise home again. So we would go to the near-Earth asteroids. Then we looked at types, families, and colors. Last thing we'll talk about is a little bit about the surfaces of asteroids, what they're like. But let's go back here. Let's look at the business end for a second, the players and how much money they have. because this has all happened in the last 2 years. So that's why I say this is a momentous transition. Humanity is about to start making a living in space, and we're being driven there. It's not, we have to, because the stuff on Earth is running out. We're running out of metal. If we're going to continue a civilization where we use 2 tons of iron per human being, and that's average for the whole world, it's much higher in the first world. In America, for instance, it's like 17 tons per human being. Then we got to get more stuff. So there's this company, Planetary Resources, started up in 2012, the spring of 2012, and their mission statement says they plan to build by 2020, 6 years from now, they plan to build a fuel depot in space. Now, what fuel are we talking about? We're talking about water. If you split water apart, you have rocket fuel, of course. And it's very expensive, $10,000 a pound, to haul your fuel from Earth up out of Earth's gravity field. So if you could get the water in space and then split it with solar power, with solar panels, then you would make your rocket fuel right in space. It would save you all that $10,000 a pound would be saved. Of course, it's going to cost you something to find this water and so on, but that's the idea. So that's how they say they want to make money to start with. They recognize that it's quite a challenge to get the platinum first, so they're trying to take baby steps and work their way up. They say you have to build a whole new technology to be able to bring back this platinum. How are we doing on time, by the way? 7:25. Oh, okay, let's pick up the pace. We're supposed to bring this in under an hour. Deep space industry started in the fall of 2012, and they want to prospect by 15 next year. I assume that means telescope prospecting. Then bring back a sample the year after that, and in 9 years from now, start mining. Kepler Energy and Space Engineering just started last fall. And their distinction is they say, we're not going to build all new technology. We're going to use existing technology. That'll get us into the race faster. We'll hit the ground running. Of course, the existing technology isn't very good, so it's going to be expensive. So you got a trade-off there. They want to bring back 40 tons of rock in 6 years from now. My money's on these guys because they're financed by billionaires, it turns out. These guys are scientists and engineers, no cash. So let's concentrate on Planetary Resources. Let's have a quick look at this crowd. And here we have Larry Page. He doesn't know how to hold a microphone. He is one of the founders of Google. And Eric Schmidt is the CEO of Google. Richard Branson, you may know from originally Virgin Records, got started in the record business, then Virgin Airlines. Now he's into space companies. Ross Perot Jr., actually is a rich boy, made his money from, his dad actually made the money in computers. You see a trend here, computers, computers, computers. That's the modern railroads. You know, these are the, probably shouldn't say robber baron because this talk is being recorded on archives. But anyway, Ross Perot Jr. also made his own money in real estate, but you know, he had a leg up. His dad's worth several $1 billion. Ram Shriram is Indian, and he started off on Netscape, computers again, and then was on the Google board. Charles Simonyi, Microsoft. James Cameron, now he's the standout here. He's also a billionaire, but he made his money in movies. Let's see, he started off with Terminator, and then Aliens, and then Titanic, one of the top 2 grossing movies of all time. And then Avatar, the top grossing movie of all time. Number 1 and 2 movies of all time. This guy made a lot of money in Hollywood. These two are employees. They are not billionaires. Sarah Seeger is a scientist and astronomer at MIT. And Tom Jones is an astronaut, also a planetary scientist. Let's concentrate on the 7 billionaires here. They say they want to spend $1 billion on their company, Planetary Resources, to get started. Can they do that? Yes, they can. Larry Page is worth $30 billion. Eric Schmidt is worth $8 billion. Richard is $5 billion. Ross Perot Jr. is $2 billion only. But his dad has $4 billion, so the family, $6 billion, not doing too bad. Ram Shriram, $2 billion. Charles Simonyi, $1 billion. James, $1 billion. Total, $50 billion. They can spend $1 billion like small change. By the time they've spent that, they'll be worth a lot more. So if they need to put another billion in, no problemo. We're running out of time. I wanted to mention the iconography in these that's interesting in these pictures. Let's say you were just 1 minute on this. Let's say you were a Martian and you landed on Earth, and this was all you knew about companies on this planet. And you looked at these 7 investors. These guys own the company. These are hired hands. Well, one thing you notice is they are all male. Now, what are the odds of that? And this is an interesting point. It's not just a sociological point I'm making here, but it's also about how you do experiments in science. And you do an experiment, you gather data, right? But then how do you decide what your data means? That's equally important to gathering the data. So scientists talk about significance, right? Is the result you get a significant result, or did it just happen by random chance? Well, let's think about this. What's the chance of this person being male? 1/2, roughly. I think there's actually 51% females at birth, and then, no, that's the other way around. 51% males, but males die off a little faster, so at the end there's more females, but it's pretty close to 50. So, okay, let's call it a half, 50-50. Now, what's the chance of 2 males in a row? This is like, flipping a coin. Well, half again. 1/2 times 1/2 times 1/2 times 1/2, 7 times. What's that? That's 1/128th. In other words, less than 1% chance that you get 7 billionaires. These 7 guys are all males. So if you were a Martian, this is all you knew about our society, you would say there seems to be a sexual bias here. And then what else would you notice? And you'd be right, because that less than 1% chance of this happening randomly is what we is. What's that? Okay, now she's a scientist. I was trying to gloss over this point. That's true. We could have said there's the chance of 7 women in a row is also 1/28. So let's put those 2 possibilities together. It's really 1 in 1/64th chance that you get either all men or all women. But that still passes. Usually we require 95% confidence to say we have a significant result, or 99%, depending on how critical you want to be. So 1/64th, what's that mean? You're 1.5% off. So that's 98.5%. That's, we'll call it, yeah. What's that?
Not 3 sigma.
Okay, technicalities. No. Crucify me. Anyway, this is highly unlikely. Time's up. Oh, repeat questions. For online folks, I have somebody in the peanut gallery is criticizing my mathematics. And she is absolutely correct. I was trying to dance over this little section without getting caught, but she nailed me. Okay, let's take, what else do you notice? These are all white men, except for Ram is Indian. Now, what's the chance of 7 white people in a row, randomly? Well, America's mostly white people. It's like 80% white people. So the chance now would be 80% times 80% times 80% randomly. But we got 1 non-white guy. So that's, anyway, the math is a little more complicated here. I worked it out. It's about 1/3. So there's only 1 in 3 chance that this is a random assortment of races. That's not very convincing. That could easily be chance. So this, we cannot, if you were Martians and you only knew this about Earth, you could not conclude that there was racial bias in this society. We might believe that from other reasons, but from this experiment, we couldn't conclude that. Now, lastly, did I say I was going to take 1 minute on this? What's the chance of billionaires? Well, there's only about 2,000 billionaires in the world, and there's 7 billion people. So the chance of a random person being a billionaire is about 1 in 3 million. So 1 out of 3 million times 1 out of 3 million. There's the huge bias here. Apparently companies on Earth are run by billionaires. They make those decisions. Okay, there was our 1 minute I allotted. Asteroid surface, the last topic here, and we'll get out of here. Well, this is a picture of Gaspra again. We saw this at the beginning. Now this is a color photo. It's not really this colorful. This is a little exaggerated. This is enhanced colors. if you actually saw this, if you were flying up to it in your spaceship and you looked at it with your naked eye, you'd say it would look like gray or brown. I mean, there might be some very faint color distinctions. There'd certainly be brightness distinctions, but it wouldn't look, you wouldn't see these bright blue spots and so on. But what you do see from this picture is that there's been a lot of impacts. These things get hit all the time by different sizes. Typically, the size of the impactor is 1/10 the size of the crater it makes. So this crater was made by an impactor about that big, and so on. This is what did we say? This was. Oh, how big is the? It's 1/10 of that whole 1/10 of this crater. And this crater, I think we said this thing was 8 miles across. So what's that? That's about 1/4 mile and 1/4 and 1/10 of that. 1/4 mile is 400 yards. 1/10 has 40 yards. So you have 40-yard rock coming in at 5 kilometers a second. Let's say it's the speed. It's not only the mass. It's the high speed. Because remember, the energy is mass times velocity squared. So speed counts more than mass. Here's a picture of Eros. Now this happens to be an asteroid in near-Earth orbit. And this is from fairly high up above the surface. It's a very sharp picture. If it looks blurry to you, you should probably get your eyes checked. Here's a more close-up shot. Now I think on this scale, these boulders, say this boulder is several meters across. So a person laying out there sunbathing, would be that size. So what do you see? Well, the impression I get from this is it's very rocky. A lot of regolith. And, the old view of asteroids used to be that they were these solid chunks of rock flying around space. Not like that at all. We now think they are rubble piles. It's just like you took a D9 bulldozer out here and bulldozed up for a house lot. You bulldozed up a pile of rock. That pile of rock is an asteroid. And this is my own idea. I haven't heard anybody else say this, but based on my experience bulldozing for houses, not running bulldozers, but building houses, you notice when you bulldoze a lot, the first thing they do is go through, break it all. They use their claw, they break up the rock, and then they shove all the fines they get off in a pile on the side, because those are valuable. You want to save those fines, the fine material. Then you smooth out the rest, you roll it out as smooth as you can. Then you bring back the fines and use that for your top coating to get your smooth surface for your driveway and your house pad and so on. So why is that? Because if you just have a rubble pile and you shake it up, the fines all filter down. They all fall inside, and the big rocks rise to the top. The scientists talk about this as the Brazil nut effect. If you take a can of nuts and shake it, the big nuts rise to the top. The little stuff goes down. I think the same thing happens on asteroid, although this is my speculation, but I think the surface is covered with these big boulders, and the fine stuff is probably down inside. But they're rubble piles. Okay, here's Ito Kawa. The Japanese sent a spacecraft here. This is a close-up photograph. They in the zeros, and this thing is about 600 meters long. So this is the head. It looks like an otter. If you see the whole thing, like an otter laying on the surface of the water, the head and the body. So here they call it the otter. Here's the head, and the body goes farther back here. But again, you see a very rough, rocky surface. I estimated that this is the biggest rock I see there. I think that's about 20 meters tall. And you see the sun, here's the shadows. So the sun is over here, and you see all distribution of rocks. Now this head, what is inside there? Is that one big solid chunk? There might be one big solid chunk or a few solid chunks in there. But probably the head is distinct from the body here. These two big chunks, if they are two and not 12 chunks, they're probably held together by very weak gravity, as I said. So you could go here. Because of the gravity, there is inertia to these rocks. They resist being pushed, but there's no gravitational force holding them onto the surface. Very weak. So if you stood here and took let's say you take one of our standard boulders, you couldn't pick that up on Earth. No human being could pick up our cubic meter rock. But on an asteroid, you could, slowly. If you just stood there and just pulled and pulled and pulled, it'd take a while to get it started. But once it started moving, you could lift that, you could throw that boulder off the surface here and project down. In fact, you think of yourself laying here, or standing here, if you jumped, you would reach escape velocity. You would fly away and never come back. So it's a very low gravity holding you on. So you see these pictures. These people have, like, science, what do they call it? Popular science. I saw one last year. They said asteroid mining in space, and then they had this picture of this big tractor on the thing with giant wheels, and it's churning across the surface, and it's got these giant drills, and they're grinding away and so on, trying to break up the rock. It's not like that at all. You can't drive a car on one of these things. It would just, the first time you hit a rock, you'd bounce off into space and never come back. So the whole point is to hold on to the surface. And I have some ideas about that, but maybe in question period we can bring it back about habitability. More pictures. We're way out of time here. What are the key points here? Here's a... Huh? Okay. We've got little... it doesn't show up here, the little nicks, do they? Maybe that's the next shot. Anyway, here what they're showing is these are blow-ups of sections in this picture. And here's a size scale. So that's 30 meters. And this is D. Picture D comes from here is D. So this picture is supposed to be that blown up. This is on Itokawa. Still, we're on Itokawa. And again, the whole surface is rocky. So you don't have to grind anything up if you go there to mine stuff. It's just a matter of getting a bag out and filling it up with rocks. You know, it's a simple matter. There's this, they call this a pond. That just means there's some fines here. There's some sand has collected here in a low depression. And what else do we got? One more slide, I think. More rocks. What are these lines here? Oh, here's the nicks. You see these little arrows are pointing at those bright spots, and they think that's where rocks have hit the surface and nicked the rock, and it's made a bright spot, and it's bluer, and that goes back to the space weathering thing about the colors. But so these things get hit occasionally and leave little bright spots. These lines, these parallel lines here, show you the way the rocks are moving. They're on a slope, and they're sliding downhill here in this direction. And you notice that there's a typical orientation. If you see a rubble pile like a bulldozer makes, and you see that pile of grounds up, you will see the rocks, they don't go down like this if they have a length. They turn sideways, and rocks tend to slide down sideways like this. And that's exactly what you see here with these parallel lines. You see these rocks like this, and that, and that, and that. You see how their orientation is all similar. They're sliding downhill here. And more nicks, rocky surfaces. Okay, that's it. Things to consider for the future. There are a large number of near-Earth asteroids. We've now found, we just passed 10,000 discovered. And the size of those goes down to about, what's the smallest one? A few hundred meters anyway. So we still haven't explored much below a kilometer. But we have found 10,000 that are near Earth in orbits that might be accessible. And like I mentioned, my buddy Nick and I are looking for the slowest asteroids. Well, the way the engineers figure this is they talk about delta V. Delta V is velocity. Delta V tells you how much fuel you need. Basically, how much do you have to change your velocity when you leave Earth to catch this object and get home again. So you want a small delta V because it's all about fuel. The fuel is what's expensive. So you want to minimize the amount of fuel you use. So you're looking for the smallest delta V objects. So a very small delta V would be like 5 kilometers a second. Yeah, you do have to accelerate a lot. But I mean, some things are 10 kilometers, 15, 20 more kilometers a second. So, so far in this survey, which just started last fall, we've looked at how many objects have we looked at? Well, less than a dozen. We've looked at less than 10. But we're picking out, of all the asteroids that are discovered, we pick out the ones with the smallest delta Vs as possible future missions, manned missions, so we could get people there. It's not just about the fuel cost, of course. It's about people living in space for extended periods of time. You know, how long can you survive in space? You got to take your food and water along. That's heavy, and again, $10,000 a pound to get your gallon of milk into space. That's expensive. So you want to keep these missions short. So you want to find the slowest asteroid going by Earth. You want to hop on it, take a quick look, and race home again before the food runs out. Robotics certainly have a lot of advantages, but they are still not up to the level of human beings. Human beings are delicate. That's their drawback, but they're clever, so they get on site and you start finding unexpected things. They can be creative, they can innovate, they can, think. The trouble with our robots just aren't very small. We can put robots in auto factories that do the same action, 20,000 times, but we need smarter robots. Well, we have a long wish list. That's one of the things on it. Remote sensing, like we said, that's the only solution. You can't go visit all these hundreds of thousands of asteroids. Mining solutions, I got ideas about that, but we're running out of time. Delivery problem, that's the $10,000 a pound. If you did find solid chunks, here we go. Oh, we have a sample. Oh, well, what is this? Model. This is a model of comet 9P Temple 1. There you go. That's a shape model. So they've done detailed images, and they figured out the shape of this comet, and there it is. That's the actual shape. If you did find a bunch of platinum, let's say, okay, what do we say? Every year we produce 200 tons. Let's say we found 200 tons. Well, that's going to crash the market, right? The price is going to drop to half or whatever. So that's a problem. Although it might be compensated because when the price of something drops down low enough, then people find new uses for it. It's like, oh, well, it's a lot cheaper now. We could do this with it. Yeah. So that could be it. And then habitat, I got some ideas if you want to ask me in the question time. I think we have like 10 minutes or however long for questions. And just 1 second, I'm not sure if, are we able to take questions from people online too? Hayden? Okay, so people online, hello. If you have a question, email him to Sifan. He is in California. And he will tell Hayden here, and Hayden will tell me. Habitat. Okay, one line. Let's say you want to live on an asteroid. How would you do it? You see the popular science version is you go there, you build factories, you mine your ore, you smelt your metal, you make your fat, whatever. That's not going to happen. But what about this? Tell me where I'm wrong on this. This is my own idea. You pull up next to your asteroid. Park. You throw out 3 ropes. You lash them onto the three biggest boulders around to hold you there. And then you open your bottom hatch and you take out your aluminum tube you've brought along with you, and you have a winch, and you start cramming that aluminum tube. You start cranking it down into the asteroid. Now remember, the asteroid is made out of heavy rocks. They're hard to move, but there's nothing holding them together. So you just push slowly. You're holding on to the 3 biggest rocks, so you're not going to move. You start cranking your pipe. Here's your pipe. You start cranking it down into the inside. Goes slow, but it slowly winches down. You winch it in 10 meters, 20 meters. Then you pop it open. It turns out it cracks open, and inside you have a balloon, and you blow up your balloon. You have an air compressor. So you blow up the balloon. Now again, it's a weak balloon. You think, well, how's that going to push big boulders apart? Well, because there's nothing holding them together except this microgravity. So you slowly inflate your balloon, and it slowly nudges the boulders apart, little by little. Might take a few hours, but pretty soon your balloon blows up. You unzipper the end of the balloon, go inside, close the hatch behind you, put out your solar cells on the surface. Now you're inside the asteroid, so you're protected from solar radiation and so on. It's full of air. You got your solar cells on. You turn on your heater. It's nice and warm. You pull out your electric guitar and rock out. Home sweet home. So that's my idea about habitat on asteroids. Something like that would be cheap. Kevlar balloon, that sort of thing. You can't build buildings and all that. I mean, there's nothing to hold them down. Yeah. Sorry, I missed you.
It seems to me that they would want to build a permanent floating station going just a little bit slower than the general population of boulders, and catch some of the ones that seem reasonable as they come by, and slowly alter their orbit in such a way that they kind of just fall towards Earth.
They would and they will build stations. We already got one station going up there. It's permanently occupied. Oh, repeat the question. The question is, why couldn't we build a station and slowly just pick up the boulders coming flying by? The problem is they're far apart. That picture we saw looked like there was a whole crowd of boulders. But if you were actually out there, you get to one asteroid. The nearest asteroid is 1,000 miles away. You know, it's a long ways away. You're gonna sit there for a year. You won't see anything go by. They're not. It's not like Star Wars when they fly into the boulder field. You know, they're dodging around. It's not like that. It's here's one, and 1,000 miles there is another one, and so on. So they're really spread out. Yep. Ownership. We have a question about ownership. Well, as I said, for this historical... That's probably how it works. This is capitalism for the last 5 centuries, so assuming capitalism continues for a little longer, for better or worse, at the moment it would be, there's no law, there's no space law really, so it's first come, first serve. It's like the California gold rush. You stake a claim and you guard your gold with your 6-shooter. I mean, the difference is there's no people in space, so there's nobody to guard it against, but I assume, like Planetary Resources, if they find their platinum boulder, they'll just bring it back to Earth and sell it. And who's going to challenge them? I don't know. They would have the backing of the U.S. government, I assume. This is Silicon Valley, very tightly integrated with the government. So if they have the U.S. Army behind them, who's going to challenge them? You know. Yep. Okay, the comment is that this is very similar stage that we're transitioning through now to the exploration of the New World when the Spanish Columbus got here, and that's true. It's a huge expansion of human endeavors. Of course, it might not work out. It might turn out to be way too expensive. It could be a total bust. But let's say it does work out, then this is the beginning of a new age. The big distinction is that Columbus was a brutal guy. The Spanish Empire was brutal, and so there were people there that owned the gold that they wanted to get. Those people had to die. The nice thing about space is there's nobody there, so you don't have to kill anybody. And even you could even bring up, similarly, you could bring up ecological issues. But ecology deals with life on Earth. You know, we go to some island and despoil it. But there's no life in space, as far as we know. And so, can you wreck an asteroid? It's already a rubble pile. What more can you do to it? You know. So, in some ways, it's not like traditional imperialism, you know, that's gone on for many, many centuries of countries invading and slaughtering the natives and taking their resources. We bypass all that. That's not an issue this time, for once, which makes it a lot cleaner enterprise. You don't have the moral qualms you have to deal with. Yep.
You say anything about citizen science and NASA's Asteroid Grand Challenge?
Am I involved in it?
Do you know it? Can you say anything about it?
The question is, do I know about citizen science and the NASA challenge? I don't know anything about it, I'm sorry to say. Well, the question is, how do you actually go about doing this mining? Do you just grab a boulder and pull it into the hatch and fly home again? If you find the platinum standard boulder, yeah, I think that's more or less what you do. If you don't find that and you just have ore, it's probably not feasible to bring ore back to Earth. It's so heavy. These guys, the third company there, they wanted to bring back 40 tons of rock. You know how much that's going to cost? So then people say, well, okay, you don't bring it back to Earth. You use it in space. We're going to build a city or build whatever. We're going to build fuel depots, build, stuff in space. So instead of hauling the iron out of the Earth's gravity field up there, we'll just get the iron there. We'll smelt it there. We'll make stuff there. Pretty sketchy. That's hard. I think you go for the jackpot strategy. I haven't heard anybody else talk about the jackpot strategy. This is my own ravings. What are the chances that there are actually solid chunks of platinum or gold or something? I don't know, but I think there's enough chance for me to get up in public and say these things, and nobody can contradict me. Yeah. Here you go.
Yeah, no. So, okay, that's a very good idea. How are you actually going to find? How are you actually going to find the platinum in amongst the rubble? Because I still haven't quite seen that.
Okay. So my jackpot strategy requires that there be a chunk of platinum floating free that we look at through a telescope and we see its spectrum. Then we say, hey, look at that, let's go get it. If it's the rubble pile, if it's on Itokawa, and Itokawa is the remnants, it's a reaccumulation of a formerly destroyed asteroid that fell back together, all the chunks. And inside there is our platinum boulder we're looking for. Then we've got to go to Itokawa and dig through the rubble. But remember, now we're in our tent underground playing our guitar. So every day we dig a little deeper and we make tunnels and we go and we look and oh, what's this? And then we find it that way.
Why not just stick a dynamite in the middle? One stick of dynamite, no rubble. I'm serious.
Yeah,
You
nope.
take a rubble pile apart, you'll be able to look at
That's right. Well, these rocks are still heavy. You can move them, but they have a lot of inertia. It's still like a mountain there. You can't blow up a mountain with one stick of dynamite. So you need a lot of dynamite, and then you have to haul that dynamite up there. And remember, $10,000 a pound. So, yep.
How long would it take to get to a near asteroid, find a boulder of platinum, and bring it back?
How long does it take to get to the asteroid and bring back the platinum? Well, you could get there. Let's see. How long did it take them to get to the moon? A week? 3 days to the moon? This is harder. These things are going, the moon is pretty close and going very slowly. These things are whizzing by, so we've got to accelerate to 5 kilometers. We need big rockets. We blast off. We know it's coming. We launch. We try to match our trajectories. We pull up next to. How long does that take? Weeks? I think it takes weeks to get there. Now we're going to do the job. We got to dig around for a while. I mean, the first time you send men there, women, whoever, whites, blacks, we're going to have a ecumenical crew. I hope, like Star Trek, Star Wars. We'll have some weird-looking creatures. The first time you go there, you're just going to take a few samples and race home. Then after a while, you do a few things like that. So eventually, though, you're going to stay for months. Now, the thing is, the asteroid, you hop on the asteroid, it departs the Earth's vicinity. And it's a year before you come back. I mean, it takes the Earth a year to go around. And the asteroids, well, these are near-Earth asteroids, so it also takes them a year. So do you want to commit to a year to live on your ship to get out there and then come around on the other side and get home again? That could be up to a year. So they talk about missions they talk about the 90-day mission, the 180-day mission, the 1-year mission. And then they calculate how much fuel you need for each mission, and it escalates rapidly, obviously. And you also need food and water. So it gets really expensive real fast. I don't know. In the current economy, I think what we're looking for in the next, 2014? What did these guys say? They said 2020, that's, they're optimistic. There's a sales pitch. So, yeah, it's the 30s, this is 20 years away at least. And then we probably start off with a few month missions, 3 to 6 months like that. You go out there, probe, come home. It's not for the faint of heart, the asteroid mining business. Yep. No questions from the virtual audience. Okay. Good night, virtual audience. We have a question here, though.
Families of asteroids, there are some that are, they believe maybe more ice water based, or is it all rocky?
No, yeah, there are different types. Okay, the question is, what are the differences between the different types of asteroids? Well, the big two groups. The S types are the ones closest to us. That stands for silicates. Then the inner main belt, those are the ones, most of the meteorites that fall on Earth are from S-type asteroids. They're rocky. They're like, in fact, they're primarily two kinds of rock, olivine and pyroxene. And if you go to the South Point on the Big Island, you will find the green sand beach. That, I don't know if you've ever been there, but it's kind of a khaki green. That's olivine. And that's an extrusion from inside the Earth, came up. A lot of the mantle of this planet is olivine. Then there's pyroxene, it's black. But if you look at C-type asteroids, they're called carbonaceous. They're very dark, very low albedo, only about 5% reflectivity. And they're a different kind of rock. If you look at M-types, those are metals, they believe. And that's where the iron meteorites come from, chips off of those. So those are going to be solid iron. Solid iron nickel, and who knows? Maybe that's a good place. Maybe inside an M-type is where we should be looking for our mother lode of platinum. Of course, now how do you dig down? Uh-oh. Here comes a question I fear, Jeff. Okay, question is, it's lately been commented that asteroids have moons and even rings around them. What do we know about, you're saying, the composition?
So that tells us how we can measure.
Oh, yeah. So the point is, from the mechanics, so from physics, you can then tell the mass from looking at it and getting the size, if it's big enough to measure in a telescope. And then if you know how fast things orbit, you can tell how much mass is there, and then you can determine the density. So that's correct. But we already have a pretty good handle because we can just look at meteorites. We have stones and irons, and we know the stones are 2 to 3 and the irons are 8 and so on. So how much, yeah.
But the idea is, do we have the possibility, now that we know that there are rings and that there are moons, of surveying a large number of these asteroids without having to go there, by knowing their density?
Well, yeah. Yeah, so from anything that has a moon, we could determine a precise figure for the density. And let's say it comes out to 4. Then we know it's like half rock, which would be 2.5, and half iron, which would be 8, and so on. So he's saying you could figure out the proportions of metal versus rock and so on. And that is true. That's correct. Now, how many have moons? I don't know. Pluto, for instance, is not an asteroid. It's what are they calling it now? It's a dwarf planet. It's got 3 moons. They keep finding more. We're up to 3. Dave Tolin, actually, that I mentioned here. 5 moons. 5 moons. I stand corrected. There's no end to it. Dave Tolin is an expert on Pluto. He looks at it all the time. He carefully calculates the orbits of the moons. Moons are pretty common, apparently. Like Jupiter, Henry Shea was a grad student at IFA. That's what he studied, and Dave Jewett was an astronomer there. They found Jupiter has, at last count, it has 60, 80, it's a huge number of moons. It's ridiculous. Saturn, same thing, 30, 40, 50 moons or something. So moons are pretty common in all size scales. Is that about it? We're wrapping up. JD says keep going, but you always want to leave them wanting more. You don't want to talk people into utter boredom. So you can't see. Are there any more questions? No questions online. I think no more questions in the audience. I think it's a wrap. Thank you very much.